Hey guys, today we are going to go through our last section for polar functions and polar things by today connecting what we did in the last section, which was talking about complex numbers. And we're going to now take complex numbers and marry them with um, polar functions and polar numbers and polar coordinates and equations. And we're also going to talk about a pretty famous theorem that should make it easier to raise complex numbers to higher powers by using the polar form of a complex number. And that theorem is called DeMoivre's theorem. So today we're going to mostly convert complex numbers from rectangular to polar form back and forth, and we're going to do some products, some quotients, and powers of complex numbers in polar form because it's a lot easier to do in polar form than it is in rectangular form. All right, so let's kind of go through this a little bit and see what we're talking about here. The first thing we need to kind of discuss is what the modulus of a complex number is. When we were talking about real numbers, we have a thing called absolute value. For an absolute value, you just go how far away is a function from the center? How far away is it from the origin? If we're talking about a number like 4, it is 4 units away from the origin. When we talk about a coordinate point, 3, 4, and we want to talk about how far it is away from the origin, we can do that as well, right, by using Pythagorean theorem. With a complex number, it's just a single number, right? You'd think it'd be more like absolute value, and it is in a way, but what we call this is a modulus. A modulus, anytime we're using this kind of absolute value thing, this is really what we refer to as a modulus. And a modulus is how far away from what's the magnitude of this particular number, right? That's kind of what modulus stands for. So to find that when you have some complex number a plus bi, if we think about an Argand diagram, right? So if I had 3 plus 4i, right? And so I come over 3 and I go up 4 on the imaginary axis, and I go, how far away from the origin am I? Well, I can do this by using Pythagorean theorem. Over 3, up 4, and we can then kind of find the hypotenuse of this thing, which we would do by squaring the a, squaring the b, adding them together, and square rooting. And the modulus of this particular number, right, 3 plus 4i, is 5, because it is equal to the square root of 3 squared, which is 9, plus 4 squared, which is 16, and that is going to be equal to 5. So that's where we get the modulus from. The modulus is how far away from the center our complex number is when we plot it on an Argand diagram. So that's what modulus is for a complex number. So that's that definition for you. So let's find the modulus of some following complex numbers. I already just did this one, but we'll redo it, and this time we'll do it a little slower. So if I want to find the modulus of that, I'm going to call that, putting this around there, the little absolute value sign, right? That is the square root of the a squared plus the b squared, square rooted, which is the square root of 9 plus 16, which is the square root of 25, which is 5. Or what about this one? What is the modulus of negative 2 minus I? Well, my a here is 2, or negative 2, excuse me, so negative 2 squared, plus my b is negative 1, so negative 1 squared, so the square root of 4 plus 1, which is the square root of 5. So my modulus is root 5. Okay, so this is pretty simple to calculate. It's really just doing a Pythagorean theorem. Let's talk about polar form of complex numbers. So we've already talked about the modulus, right? And we're going to need that to be able to convert these things from rectangular to polar. We're also going to need an angle. So if you kind of think about what polar was an r and a theta. Okay? And we just found the r, the distance from the origin, on the Argand diagram. We call that the modulus, right? So the modulus is going to be part of the polar form of a complex number. The other part of it is going to be right here, this angle. And we're going to find the angle the same way we found angles when we were dealing with things in polar, going from rectangular to polar with coordinates and stuff. But for this, we sometimes is known as the argument, okay, of the complex number. So sometimes this angle is called the argument. So if you ever see that phrasing listed out there, just know that the argument is the angle, the modulus is the distance away from center. All right, and as we did with polar, we saw that it was the inverse tangent of the y over the x, or in our case, the inverse tangent of the b over the a. When our a's are positive, we have to add a pi in there when our a's are negative because of the range for inverse tangent. Inverse tangent only gives us values between negative pi halves and pi halves, so we're missing half of the angle. So when we're on the second or third quadrant side, we have to add pi to get to the right spot. And here's the polar form. It's the following. We get the modulus of the z times the cosine of theta plus I times the sine of theta. Why is it that way? Well, if you think about it, how can I get to A? Well, if I know theta and z, right? Theta and absolute value of z, then I know that the cosine of theta is equal to A over the absolute value of z. And if I multiply that z over, you'll see that this is equal to A. So you can see if I multiplied this modulus in, I'd have right here z, the absolute value of z, or the modulus of the complex number z, right, times the cosine of theta. And that would be equal to A. Down here in the back, similar fashion, if I was trying to solve for b, I can say that the sine of theta is b over the modulus of z because of trig, if you look over here at this triangle. And if I solve that for b, I'd get the absolute value of z, sine of theta is equal to b. So again, if I multiply this in, then I'd have bi. So there it is, a plus bi written in a polar form. Okay, so that's what this is. It's just you put the modulus on the outside, cosine of the argument plus I times the sine of the argument, and there we have it, the polar form of a complex number. So let's look at how we could do this in practice, okay? So let's convert this one from rectangular to polar. First thing I need to do is find the modulus. So the modulus of this number is the square root of 36 plus 64 when I square my a and my b. That should be 10. Then I need to find my argument. So my argument is, my a here is negative. So it is going to be the inverse tangent of 8 over negative 6 plus pi. Now for this, if I were you, I would find a calculator. And mine is apparently walked off. I blame small children. Huh. It really did walk off, I guess. They like to press the buttons, so this thing is in degrees, unfortunately. I'd like to get my answer in radians, so I'm going to come off to the side real quick. I guess I will do it in degrees. That'll be fine. We'll just do it in degrees. So I'm gonna kind of do this in degrees. So here's this very simple scientific calculator that I was able to commandeer. Hopefully it works okay. And we're gonna take 8 over 6 negative 8 divided by 6 negative, and we're gonna inverse tangent that plus, and then instead of pi, since I'm in degrees, I have to add 180 degrees. This gives me 100, I don't know if you can see this, 126.869 degrees. So I guess we're gonna do ours in degrees, although I would prefer you to have your answer in radians for me. I just don't, I don't have the time to convert this thing in on this video without having to restart it. So uh, we've got our theta is 126.87 degrees. I guess I will also convert this into radians by multiplying by pi and dividing by 180. So I'm going to multiply this by pi and then I'm going to divide it by 180. And when I do that, I get, as you can see, 2.214. So we're going to call this or 2.214 radians, okay? So I'm going to write this in radians, and so the way I'd want you to write this is it's the absolute value of z, remember, times the cosine of theta plus I times the sine of theta. So sometimes this is called cis theta. I've seen people write it like that. Please don't write it like CIS theta. I want to make sure you understand what that stands for, but that might help you remember the way it goes, that it's CIS theta, so cosine, then the I sine. I'd like you to write it all out for now. So that is 10 times the cosine of 2.214. If you're going to do it in degrees, you better include the degree symbol, okay guys? Plus I times the sine of 2.214. All right, and there we have it. I've converted this into polar. Let's do the next one. We have 4 and root 3. First thing I need to do is calculate the modulus. I'm going to change colors real quick so we can see the difference here a little easier. So this is the square root of 4 squared, which is 16, plus 3, so that's root 19, is my modulus. And my inverse tangent for my argument is going to be, again, my a is positive, so I don't need to add the pi. Inverse tangent of the y, root 3 over 4. Alright, so I've got 3 square rooted divided by 4. Then I'm going to inverse tangent that. That gives me 23.41 degrees. I'm not going to leave it like that. Times pi divide by 180. And I get 0.408 radians. So that would mean that my answer for writing this in polar form is root 19 cosine of 0.408 plus I times the sine of 0.408. All right, so there we have it. It's two simple formulas. One finding the argument right down here, right? And then one finding the modulus. Put them together into their format. Alright, it's a little bit easier actually, because it's a little bit easier generally, as long as these are numbers on the unit circle, to go the other direction, to go from polar to rectangular. First thing they asked me to do is graph this complex number on a polar grid. Okay, well that seems fine. We are going to draw a little polar grid here. Alright. Almost done. Alright, so there's 0, there's pi 6, pi fourths, pi thirds, pi halves, etc. And then we have our circles going out. On the test, guys, students of mine, I'm going to have a polar grid already drawn for you. You will not have to draw one. Okay? I know these can kind of be a pain to try to draw. So go to pi 6 and out 3. 1, 2, 3, boom. That is where this thing is. Super easy to draw because I know it's basically that's the radius and that's the angle. Right? So it's very easy to draw these. It's also easy to convert. Okay? Because now that I know those two things, think about distributing this in and then working them out. Do I know what 3 times the cosine of pi sixths is? Well, that's going to be equal to my a. Well, cosine of pi sixths is root 3 over 2. So a is 3 times square root 3 over 2. B is going to equal 3 times, if I multiply it in, the sine of pi 6. Sine of pi 6 is 1/2. So I have 3 times 1/2. And then my as b, and so my final answer would be 3 root 3 over 2 plus 3/2 I. That is what is equivalent to z. Okay. Now let's talk about, now that you know how to convert back and forth between polar and rectangular. That's going to be a skill we'll need a little later. We're going to talk about finding the products and quotients of polar complex numbers. Now, if you remember, when we did this in the last section, when we found products and quotients of polar number, or not polar numbers, excuse me, of complex numbers, we had to do a lot of distributive property when it was products, and then we had to, simplify out our I squareds and combine like terms, and it was kind of a mess. When we did quotients of complex numbers, we had to multiply by a conjugate on top and bottom, and then do the same thing where we had to use the distributive property, multiply things out, combine like terms, change our I squareds into negative ones, simplify it all down. Turns out with polar complex numbers, things are a lot easier. When we want to take z1 and we want to multiply z2, what we do is we multiply the radiuses together, the radii together, and then we add their angles. When I want to divide them, I divide their radii and then I subtract their angles. Easy peasy lemon squeezy. Okay? Very simple to do. So, here we go. Let's try to do this. We're going to find the product of the two complex numbers, and then we're going to write that complex number in rectangular form. So if I want to do z1, z2, then what I'm going to do is I'm going to say it is 2 times 4 times the cosine of 5 pi thirds plus pi sixths plus I times the sine of 5 pi thirds plus pi sixths. Notice that I'm just multiplying the two numbers up here together, and then I'm adding the angles. This is equal to 8 times the cosine of, well, let's see, that is 10 pi sixths plus pi sixths, which is 11 pi sixths, plus I times the sine of 11 pi sixths, same addition. There it is, I have found the product. Now they want me to write it in rectangular form. Again, all I have to do in rectangular form is distribute this 8 through and work out the math. So I've got 8 cosine of 11 pi 6 plus I times 8 sine of 11 pi 6. I need to find out what cosine and sine of 11 pi 6 is. Cosine is root 3 over 2. So I'm going to have 8 times root 3 over 2 plus I times, it's going to be negative 1/2. So 8 times negative 1/2. And we end up with 4 root 3 minus 4i. And that's what happens when we multiply those two together. If I were dividing, I do very similar things, only instead of multiplying here, I would divide, and instead of multiplying here, or instead of adding here, excuse me, I would subtract. All right, let's talk about DeMoivre's theorem. DeMoivre did this to come up with the powers of complex numbers. So, what he did was he said, look, if I'm multiplying a complex number by itself, right? If I take this thing where we multiply two complex numbers and I do it just multiply by itself, then instead of doing back here r1 r2, it would be r1 squared if I multiplied z1 times itself. So if it's z1 squared, it's going to be r1 squared, and then it's going to be cosine of 2 theta, right? And then if I did it 3 times, so like z cubed, right? It'd be r1 cubed times the cosine of 3 theta, because I'd be adding it all together again. And so what he did was he was able to kind of extend this out, and he was able to say, guys, this is just, if I want to raise some complex number to the nth power, I need to take its modulus to the nth power, and I need to multiply it by the cosine of n theta plus I sine of n theta. This is way easier than before. If I took this particular complex number and I wanted to multiply it out otherwise, I'm going to have to use all kinds of craziness to get to the answer. We have techniques that we've talked about in class, including Pascal's triangle, binomial theorem. You could just straight multiply this junk together a bunch of times, but none of that is going to be really what I would call enlightening by any stretch of the imagination. So instead, what I'd like to do is take this 4 plus 4 root 3i. Is that the same as we just had? Oh, almost. 4 plus 4 root 3i to the sixth power. First, I'd like to convert it to polar form. See, because when I see this, I go, that looks tough. But if I can convert it into polar form, I might have something better to deal with. So first thing I gotta do, I'm gonna find the modulus of it. The modulus is 16 plus 16 times 3, or the square root of 16 plus 48, or that is 64. So square root of 64, or 8. The theta, not this a is positive, so I can just do the inverse tangent of 4 root 3 over 4, which is the inverse tangent of square root 3. And tangent is root 3 when we're at pi thirds from the unit circle. So to write this thing in polar form would just be 8 times the cosine of pi thirds plus I times the sine of pi thirds. I want to make sure I'm showing this work for anyone who's watching my answer so that they can follow along and make sure I'm doing the right thing. So raising this to the sixth power is basically going to be 8 to the sixth power times the cosine of 6 pi over 3, so 6 times pi over 3, plus I times the sine of 6 pi over 3, which we end up with is 8 to the 6th times the cosine of 2 pi, plus I times the sine of 2 pi, cosine of 2 pi is 1, sine of 2 pi is 0. So I have 8 to the 6th times 1 plus 0 i's. So what's my final answer? It's just 8 to the 6th in this case. Sometimes they will still have an imaginary part, or maybe they won't have a real part, but they'll only have an imaginary part. It just depends on where this thing lies after we have raised it to that power. In this case, it just happens to be 8 to the 6th. All right, guys, I think this is a good introduction to this. There's some practice up on Delta Math for you all. If you have questions, of course, feel free to comment, send me an email, whatever it is that you need to do to make sure that you are going along the right track. Hope things are going well. I'll have a test review up later this week. See you guys later.